Okay, this is 13.4, video 3, the last one, and this is probably going to be a relatively long one as well. We're talking about the tangential and normal components of acceleration. Now, for those of you guys who don't like the proofs, you can probably scan through a good portion of this and you don't have to worry about it. I could really just give you these two formulas and you would be able to apply them and use them. I still want to go through and at least show where all this stuff comes from. So I'm going to go ahead and do the proofs. Again, if you don't really like the proofs, just kind of scan through to get the formulas and you can probably figure out how to do the problems. Problems themselves actually don't take very long once you have the formulas, but developing the formulas will take some time. So let's say that we have some kind of a curve and we've got an acceleration off of that curve. So the acceleration might be, I don't know, in this direction, like right there. That might be your acceleration vector off of your curve. Every curve or every acceleration vector is going to have two components. It's going to have a tangential component and a normal component. Tangential component means it's going to be tangent to the curve. It's going to look something like this. And then the normal component is going to be perpendicular to the tangential component, something like that maybe. My actual acceleration probably is not drawn exactly right, but that's the general idea. So you have a tangential component of acceleration and you have a normal component of acceleration. The normal is perpendicular to the tangential, perpendicular to the curve, and the tangential, of course, is the derivative really of the velocity. So let's just write this down. This is the tangential component of acceleration and the normal component of acceleration. All right, so in order to do these proofs, in order to show you where these formulas are going to come from, we're definitely going to need to remember some formulas that we've used in the past. So one of those is going to be our unit tangent vector formula, which is r prime of t divided by magnitude r prime of t. We're also going to have to remember one of our curvature formulas. There were several different ways to do curvature, but the one we're going to use in particular here is the magnitude of the unit tangent vector divided by the magnitude of r prime of t. Not the easiest, not the best curvature formula to use, but that's the one we're going to need for our proof here. And then we're also going to need the normal unit normal vector, which was defined to be the derivative of the unit tangent vector divided by its magnitude. Okay, so let's start figuring out this thing. We're going to develop this formula for the unit normal and the unit tangential vector. So the first thing we're going to do is we're going to start off with the fact that we know that the unit tangent vector, t of t, let's go with blue here, unit tangent vector is defined as r prime of t divided by the magnitude of r prime of t. Looks like I left the extra piece of the magnitude off there. Okay. All right. But remember that r prime of t is just the velocity, right? It's the derivative of the position vector. So that's just going to be the velocity. And then the magnitude of r prime of t is just going to be the magnitude of the velocity. So taking this piece and this piece right here, I can multiply both sides of that thing by the magnitude of the velocity to get a formula for the velocity itself. So the velocity function would just be the magnitude of velocity multiplied by the magnitude, multiplied by t of t. Okay? So if I want to find acceleration, because that's obviously what we're trying to get to here is a of t, I know that I can take the derivative of velocity to get acceleration. So we can use a product rule, which says the derivative of the first is this magnitude prime times the second plus the derivative of the second, t prime of t, times the first, magnitude of v of t. All right, now's when we're going to start doing a little bit of our substitutions here. T prime of t, we can go back up to this one right here, this guy. And I can solve that for t prime of t by multiplying both sides by magnitude of t prime of t. So t prime, this blue t prime of t down here is going to be the same thing as n of t times magnitude of t prime of t. So we're going to get not t prime of t, we're going to get n of t magnitude t prime of t. Okay, and then we still have this magnitude of v of t, and we've got all the rest of this stuff. And all that still equals a of t. And we're going to do one more substitution here, which is kind of why we needed all these things. We know that the magnitude of t prime of t, we can actually solve for that one in this equation right here. So we know that the magnitude of t prime of t, if you multiply both sides by the magnitude of r prime of t, is going to be k of t r prime of t. So now we're going to get this piece to be k of t r prime magnitude r prime of t. And then we've got magnitude of v of t. Still got an n of t out here. And then I've got magnitude of v of t prime, t of t, all that still equals acceleration. All right, we can simplify just one more thing because the magnitude of r prime of t is the same thing as the magnitude of v of t, since r prime of t is v of t. So the last thing that I can simplify is this piece right here, which is going to be a magnitude of v of t. And I'm actually not going to write the entire thing out there again. I'm going to go ahead and simplify. So a of t is going to equal magnitude of v of t prime, t of t plus n of t, k of t, and then I'm going to have two v of t magnitudes, so it's going to be magnitude of v of t squared. Okay, now what we have here is we have an actual equation for the acceleration. It's not going to be a very good equation. It's not going to be really useful, but we do have one. And what I have here, I want to show you this, is we've basically got this piece right here. This is the component piece of the tangential vector, of the tangential acceleration. How do I know that? Because it's being multiplied by the unit tangent vector t of t. And then this piece over here is what is being multiplied by the unit normal vector within acceleration. So that is going to be the normal piece. Now, that's not going to be an extremely useful formula for us. It is a formula, and if you wanted to use the curvature times the magnitude of velocity squared, you could, but I'm going to try and simplify that just a little bit here. So let's look at the normal component first, because it's actually going to be the easier part. So once again, I'm going to write down that the tangential component of acceleration is the magnitude of v of t prime, whatever that means. And then the normal component of acceleration is the magnitude of v of t squared times the curvature. But we have a good formula for the curvature. The curvature formula that we used was the magnitude of r prime of t cross r double prime of t, all divided by magnitude of r prime of t cubed. But velocity, remember, velocity is the magnitude, excuse me, the velocity is r prime of t. So I can rewrite this as the magnitude of r prime of t squared. Well, the nice thing is there, we're going to get some cancellations. That magnitude of r prime of t squared is going to get rid of all except for one of those of the cubes. So what I really get for the normal component, and this is a good formula, is the magnitude of r prime of t cross r double prime of t divided by magnitude of r prime of t. So it looks very much like the curvature formula. The only difference is the magnitude of r prime of t in the denominator here is it's just to the first power. It's not cubed. This is the normal component of acceleration. Now we want to try and develop a good formula for that tangential component of acceleration. Not going to be quite as intuitive, I don't think, as this one was. So let's go ahead and go to the next page here. So again, we've got that this tangential component of acceleration, excuse me, is magnitude of v of t prime, whatever that means. We'll start off with that. Okay. So we're going to start off with, and this is where the non-intuitive part comes in, v dot a. We take the velocity and we dot it with acceleration. Well, that would just be the velocity vector dotted with. Now, the entire acceleration that we came up with was the magnitude of v of t, and I might be writing this in a slightly different order, but it's the same thing, times the curvature times the normal vector plus magnitude of v of t prime t of t. Okay, so we're going to change the velocity. Now this one you do have to go back up to the previous page. We have a formula right here. That formula right there that we can use. We could solve that again for velocity. So velocity is going to be magnitude of v of t times t of t. So I'm going to change this velocity to be the magnitude of v of t times t of t, dotted with this entire parentheses, which I guess I'll go ahead and write again. It's only time after all. Hopefully I did not make any mistakes there. Okay. So now if you remember, when you dot something, you multiply. Sorry about that. I had to pause the video. Come back. My phone started going off there. It would have been all over the video. Okay, so we're back to the dot product idea. So I guess I should probably even back up even further. Remember this magnitude of v of t, that's going to end up being a scalar times a vector t of t. So this piece right here is a scalar, and then we've got our vector right here, the t of t. And within the parentheses here, what we've got is this is going to be a scalar, curvature is a scalar, but this piece, this n of t, is a vector. So really I've just got coefficients out in front of each one of these vectors, and this over here is also going to end up being a scalar, and then this piece right here is a vector. So what we've got is a property for dot products that says if we had like a dotted with b plus c, that's the same thing as a dot b plus a dot c. Okay, it's a distributive property. So we can utilize that when we're going through this. All right. So what we're going to have is, let's see, we're going to have magnitude of v of t times the magnitude of v of t squared. So we're going to get a magnitude of v of t cubed. Remember, those are coefficients, times the curvature, another coefficient. And then we're going to have n dot t, or t dot n. T of t dot n of t. Okay, and the stuff outside there was coefficients. And then we'll distribute. So we're going to get, let's see, it looks like we're going to get, and there's no way to really simplify that one, v of t magnitude times magnitude of v of t prime. And then we're going to get t of t dotted with itself in parentheses. There we go. All right, so this is good. This works out really nicely, and because the unit tangent vector and the unit normal vector are perpendicular to each other, you should remember that when you dot two things that are perpendicular, it is 0. That whole term there goes away. Wonderful. This one over here says that I'm going to take the unit tangent vector and I'm going to dot it with itself. Well, if I take a unit tangent vector, which means it has a magnitude of length 1, and dot it with itself, you should hopefully remember that if we have a vector dotted with itself, it's the same thing as the magnitude of that vector squared. Well, the magnitude of each unit tangent vector is 1, so that whole thing simplifies to 1, which means what we're going to get here is that v dot a is going to end up being magnitude of v of t, magnitude of v of t prime. So to solve this thing, because ultimately what we're trying to solve for is this magnitude of v of t prime, I'm just going to divide both sides by the magnitude of v of t. So what I get is the magnitude of v of t prime, which is the same thing as the tangential component of acceleration, is going to be v dot a over magnitude of v. Okay, and we can actually simplify that a little bit more because v is the first derivative of position, a is the second derivative of position. So really what we get on there is r prime of t dotted with r double prime of t divided by the magnitude of v of t, but remember v of t is r prime of t, so it's magnitude of r prime of t. So this right here is the formula that we're going to use for the tangential component. And what makes these nice is in both cases, all you need to find is r prime and r double prime, and then you can pretty much fit everything else into this. All right, this video is also running long, which was kind of expected. So I'm going to skip the part about the circle idea. I might come back and do a separate video just finishing that one off, but I want to do example 6 at the bottom here just to show you that this really isn't all that difficult to do. Okay, so let's see. We want to find the tangential and normal components of acceleration vector given as r of t equals 3t minus t cubed I plus 3t squared j. So let's go ahead and write down our good formulas here for this. Our good formulas were that the tangential component was r prime dotted with r double prime over magnitude of r prime, and the normal component was the magnitude of r prime cross r double prime divided by the magnitude of r prime. Yes, I did not write the t's in there. I'm just taking shortcuts. Probably shouldn't do that as a regular thing, but okay. So we need to find r prime, r double prime, and we're going to need to find the magnitudes of a couple of different things. So let's start off with the r prime. R prime is going to be 3 minus 3t squared, comma 6t. Yeah, that looks right for r prime. R double prime is going to be negative 6t, comma 6. Okay, I also know we're going to need the magnitude of r prime. So that's going to be the square root of 3 minus 3t squared plus 6t squared. Let's make that look like an actual 6. Okay, let's go ahead and simplify that as much as we can. I'm hoping this works out okay. I think it does. So let's see. Foiling out that first one is going to give us 9 minus 18t squared plus 9t to the 4th plus a 36t squared. I think that looks right. So that's going to be, let's see, reordering that a little bit. That's going to be 9t to the fourth. Negative 18 and 36 is going to give me positive 18t squared plus 9. Okay, I can definitely factor a 9 out of that. Factoring the 9 out means I can pull a 3 out to the front. And we're going to get t to the fourth plus 2t squared plus 1. Oh, that's wonderful. Because t to the fourth plus 2t squared plus 1 actually factors to t squared plus 1 times t squared plus 1, or t squared plus 1 squared, which then you can take the square root of and get 3 times t squared plus 1. That's our magnitude of r prime of t. Man, that's actually really nice in this case. All right, so what else do we need? We are going to need a dot product, and we're going to need a cross product. The dot product will be the easier part. So let's do r prime of t dotted with r double prime of t. So let's see, if I dot those two things, multiplying the first components together is going to give me negative 18t plus 18t cubed, plus the second components is going to be 36t. Okay, and we can simplify that just a little bit. That's going to be 18t cubed plus 18t. And then we're going to need the cross product. This one will be a little bit longer, but not horrible, I hope. So let's see, we're going to have I, J, K. So we're going to have 3 minus 3t squared, 6t, and because we have to do make it three-dimensional, the k components are all 0 in this case. Then we're going to have negative 6t, 6, 0. So let's see what this cross product is going to give us. If we eliminate the I row and column, we get 0. Okay, that should be expected. If we eliminate the j row and column, we also get 0. Again, that should be expected, because it should be perpendicular to both the I and the j. So let's see here. Eliminating the k row and column, we are going to get 18 minus 18t squared. 18 minus 18t squared minus the minus, so plus 36t squared. Simplifying that, 0, 0. Looks like we're going to get 18t squared plus 18. If I did that right, that looks right. And then we need the magnitude. Fortunately, there's only one component. It's the z component. So I'm going to get the square root of 0 plus the square root of 0 plus the square root of 18t squared plus 18 squared is just going to give us 18t squared plus 18 when you take that square root. So that's not too horrible. And then we just have to plug this stuff in. Now we've got every single piece that we need. So let's see, the tangential component was the dot product, which we found to be 18t cubed plus 18t divided by the magnitude of r prime, which we found, oh, that's way down here, which we found to be 3t squared plus 1. Let's see if this simplifies any further. So I know I can factor an 18 out of the top, 18t, excuse me, out of the top, which is going to leave me with a t squared plus 1, how wonderful, over 3 times t squared plus 1. So the t squared plus 1s are going to go away. Looks like we're going to get a grand total for our tangential of 6t. All right, let's check out our normal component. The normal component is the cross, which we have down here at the bottom. The magnitude of the cross, excuse me, 18t squared plus 18 divided by Once again, the magnitude of r prime, which again down here is 3t squared plus 1. So again, it looks like I can simplify because we can factor an 18 out of the top, leaving a t squared plus 1 over 3 times t squared plus 1, and that's just going to simplify to 6. So the normal component is 6, and the tangential component is 6t. I wish I could tell you they're all going to work out that nicely, but this is the general process of finding the two components of acceleration. All right, way too long for this specific unit. I apologize for the length of these videos, but that should be all.